Hello, and thank you for your interest in audio precision. While there are hundreds of audio measurements that are appropriate for any particular device, there are some basic measurements that are relevant to nearly all audio devices. This video looks at phase. In audio, the term phase refers to the relationship in time between two tones of the same frequency. To understand what phase is, first let's take a closer look at a sine wave. A sine wave has a frequency, the number of cycles per second of the vibration, and an amplitude or level, the strength or power of the vibration. Sine waves are typically represented on an XY graph with time on the x-axis and level on the y-axis. The period of a sine wave is the length and time of one cycle. One cycle is 360 degrees. The cycle of a sine wave begins at 0 degrees at a level of 0. The wave rises to its positive maximum at 90 degrees, 1/4 of its period. At 1/2 period, or 180 degrees, it has fallen back to a level of 0. The wave continues to its negative maximum at 270 degrees, 3/4 of its period. Finally, it rises back to 0 level. This point can be described as the end of a cycle at 360 degrees, or as the beginning of the next cycle, back to 0. Two sine waves of the same frequency are said to be in phase if their cycles begin at the same time. If one wave begins at a different time, the signals are said to be out of phase. Phase shift is often not audible unless the two or more channels in question are combined. In that case, there will be addition or subtraction of signal level, varying with frequency. For a single sine wave at a particular frequency, the result will only be audible as a level change. For complex waveforms, some frequencies will be amplified and some will be attenuated or even canceled completely, affecting the frequency response of the combined signals. What can cause phase shift? Delay of one channel in a circuit will shift the phase of the audio relative to an undelayed channel. Filtering in a channel, which in analog audio is a consequence of reactance, inductance, or capacitance, and in digital audio can be a consequence of DSP filter processing, will shift the phase relative to an unfiltered channel. A polarity fault in a channel, whether caused by reversed wiring, an inverting amplifier, or poor design, will shift the phase of all frequencies by 180 degrees relative to the reference channel. APX 500 has a simple phase measurement that provides an interchannel phase meter result at a selected frequency referenced to any available channel. You also measure phase response using the acoustic response, continuous sweep, multitone, and stepped frequency sweep measurements, but we'll keep it simple and just use the meter. We've connected an APX 585 to a 4-channel equalizer using the analog balanced inputs and outputs. The EQ has rather drastic settings, which should provide some dramatic phase shifts. Choose interchannel phase from the navigator. We'll leave the generator frequency and level at the defaults of 1 kHz and 100 mV. Settings specific to phase are reference channel, where we set a channel as the phase reference, and meter range, where we define the way that we want to view the phase results. Plus 320 degrees is the same as minus 40 degrees, so you must tell the software how you'd like to see it displayed. Once again, we have accepted the default. We'll keep meter range set to minus 90 to 270 degrees. We turn the generator on and look at the results. There is nothing shown on channel 1 because channel 1 is our reference channel. Channels 2, 3, and 4 show the phase difference results. To see the actual waveforms, turn on the scope signal monitor. You will see all 4 channels displayed, and any significant phase offset will be visible. We have discussed an interchannel phase measurement and made a measurement at a particular frequency, 1 kHz, providing a simple meter result.